Good afternoon, good evening. I'm Phil Weikstrom with the Office of CTO here at VAST Data, and today we're going to be talking about VAST networking, how we go through and do it, and how we configure VIP pools and DNS and client access. So let's get started. Share my screen here. All right, so we're going to be talking about data access and data network access. So we're going to cover off, first off, we're going to talk about VIP pools and CNode pools, how we go through and utilize these to present data out from VAST clusters out to clients. We'll talk about the VAST DNS service, how we utilize that to help do load balancing for clients coming in to access the data. We'll talk about the different client access methods that are available for clients to access the VAST data services, not only standardly, but to go through and be able to implement high-speed connections to utilize as much bandwidth, as much connectivity as they have to give us the best performance. So let's start out with a real quick VAST architecture overview of the system. It's going to be a very high level of things. So VAST utilizes what's referred to as a DAYS architecture, a disaggregated share everything architecture, and it basically consists of three different sets of components. So in the back end, we have what's referred to as a D box, and the D box has two or more D nodes in it. The D nodes function independently of each other, but a D box, effectively, if you look at it, is just a JBOF. It's just a bunch of flash. It contains not only the storage device, or it contains some hyperscale flash on there, as well as storage class memory, which we utilize. The storage class memory as a write buffer, and as well to go through and store things like the state of network connections and any metadata we're going to be utilizing across things like file system permissions, so on and so forth. On the front end here, we have referred to as CNodes. The CNodes are the compute nodes. This is what clients will interact with. This is what's responsible for presenting out the storage protocols to the clients, be it SMB, be it S3, or NFS. As well as responsible for managing the cluster and processing data as it comes in. In between this, we have a high-speed network. Basically, we're using NVMe over Fabric for access between the C nodes and the D nodes, and this is done over a pair or more of high-speed switches for that. So the two connectivity options we typically have for clients are going to be either a host-based connection, which will go in via the switches. So clients would connect, you'd have your client network connect up to these internal Fabric switches. Based on how we segment the switches, the clients on your host network, on your network, would only see the C nodes, would only interact with the C nodes directly. They would not see and would not interact with the D nodes directly. They only see the C nodes, and only see the protocols established there. This is typically done on smaller networks and smaller clusters where maybe we don't need to have as much performance, or we have limited availability of those high-speed switch ports outside of the VAST cluster itself. So it makes sense. There are some limits with the performance options that you can do with this kind of a setup. So we don't, this isn't used for larger clusters, so only smaller scale clusters. And there are, as I said, some performance limits with this here as to how large we can scale for that. The more common option, and this gives us better scalability, better throughput, is to go through and have a second NIC in each one of the C nodes, which is going to be facing the northbound traffic, which is going to be facing the client to connect up to the client networks, where each one of the C nodes would be plugged into a separate external switch that the clients are set on. This allows us to go through and give us as much scalability as we can utilize for this. So we have many more C nodes on it, a lot more bandwidth for it. We're not restricted by just the physical limitations of one particular switch. We see this with larger clusters. It gives us the most flexibility for that. It's generally the preferred option if we have that, or we're looking at expanding existing clusters. So when we're talking about network connectivity within VAST, we will go through and we'll make use of what's referred to as a VIP pool. So when we go through and we create our shares or our NFS exports or our S3 buckets, which we collectively refer to as views, these views are presented out over a VIP pool. We don't directly present them out over individual IP addresses. We present out as a VIP pool, and a VIP pool is composed of multiple IP addresses, which are then spread out across the CNodes. The CNodes, when they get an IP address for that, that IP address is going to remain on that particular CNode. It's not dedicated to that CNode, but it will be assigned to a CNode, and that's all done dynamically. So as we go through and we add additional VIP addresses or we add additional CNodes, we can distribute those IP addresses out across each one of those front-end CNodes. Now, the best practice is for when we're sizing our VIP pools is that each one of these CNodes does act independently. Again, they have multiple NICs on those. If we step back here real quickly to the architecture of this, you see here that these CNodes have two separate NIC ports on each one of them for the front end of the northbound network. So we don't typically go through and do things like LACP or other types of network aggregation on those front-end ports, because it's not always the case that the switch that we're connecting to supports that, but also it can introduce some interesting, some interesting characteristics in terms of how the network hashing gets done across those. So these ports on the CNodes are going to be just straight, direct single ports on there. As such, we will assign a VIP address. We'll put one address on each one of those ports. So the best practice when we're sizing our VIP pools is we're going to have at least 2 to 4 VIP addresses per CNode in the VIP pool for as large as that VIP pool is. So the 2 addresses should be fairly obvious because we will assign one IP address to each one of those NIC ports, so we can make use of both of those NIC ports. Where we would go to 4 addresses would be in the cases of if a CNode were to go down, either be for hardware failure or NIC failure or somewhere upstream, blocking access to that CNode, or if we're taking it down for maintenance. This allows us to go through and distribute out the load that CNode was covering and move those VIP addresses out across other CNodes such that we're not doubling the workload that one CNode is handling. We're only giving other CNodes maybe half of the workload that one was taking up. The CNodes themselves can support multiple VIP pools simultaneously. We can support as many as we need to have. These VIP pools can be different VLANs, different networks. It doesn't really matter, but they do happily support more than one VIP pool per CNode. And we'll talk about why you may want to go through and do that in a moment. When we create a VIP pool, it's very straightforward for going through and creating a VIP pool within the cluster. Within the VMS GUI, or this can be done via the REST API, it can be done via the VCLI. The concepts are all going to be the same, but we would go through and provide the VIP pool with some information. So first off, we give it a name. This is just going to be a logical name that we're using internally to identify what its purpose is. We may call this the main VIP pool, or we may call this the replication VIP pool, or the InfiniBand VIP pool. Whatever we want to call it doesn't much matter for this. It's just referenced internally, so when we see a listing, that's the name we're going to use. We'll provide some network-specific information either for IPv6 or IPv4 related to the network that this is connected on, like the gateway that's going to be used, the subnet mask that is going to be used. If we need to use VLAN tags on the ports, we can go through and use the VLAN tag. If I leave this blank, it's just going to use the native VLAN. So whatever the switch is using is what we'll be using too. And there's some other information here we would go through and provide for this, but I'll explain here in just a moment. Once we have the VIP pool established, or we go through and we define the name of the VIP pool, then we need to apply and define what the IP address range is that we're going to use. So again, a VIP pool is a collection of IP addresses. Typically, we'd want to have these as concurrent ranges of addresses. So we would specify the start IP address and the end IP address, and the VIP pool would contain all of the addresses in that. Now, if we don't have concurrent IP addresses for the VIP pool, we can add multiple ranges by just clicking this add IP range and adding in the second range. If we are just putting in one address, for a couple of single addresses, we would just put the same entry for start and end for that. Once that's done, we would just go ahead and hit create, and the VIP pool would be created and be presented out. Now, where the VIPs actually get assigned is going to be determined by VMS. VMS will distribute these VIP addresses out across all of the existing CNodes that are there, or the CNodes that we define specifically to use this. We really don't care where they are, and we don't typically determine beforehand where these are going to reside. If we want to see where a particular VIP resides, we can click on the virtual IPs under the network access tab in the GUI, and we'll see the listing of the VIP addresses that are there, what VIP pool they are part of, and which CNode they are currently residing on. So in this case here, we got a VIP pool called main with addresses of 172.201, 200.203.1 through 172.203.8, which are spread out across 4 different CNodes. And we see that generally, in this case here, we've got 2 VIP addresses per CNode balanced out and spread out across all of those. So again, we really generally don't care where the VIP addresses reside in terms of the CNodes, but if we need to look at where they are, we can see that from here. So let's talk about CNode pools. So we may have situations where we want to take these VIP addresses, we want to take this pool, and we have reasons for separating things up. Maybe we've got 2 different physical network segments, like you have an example of, one example might be you're on a university and you have your HPC cluster that is accessing data on a VAST cluster, and you also have your campus-wide network. These are physically connected to different networks. They are physically isolated from each other, or you may want to go through and dedicate certain CNodes to strictly for the HPC cluster workload, so that those are always available for that and not affected by I/O that's being done on the campus network. So you can do that to provide this kind of isolation where you would dedicate certain CNodes to certain purposes and certain VIP pools. And this gives us a very crude or very crude way of doing quality of service guarantees for that. We do have other methods of doing quality of service through network and throughput, but this will give us guaranteed performance on that. We may also want to go through and do some of this server pooling, these CNode pools, because we're dealing with different network technologies. So a VAST cluster is perfectly happy to have some CNodes that are connected to clients via InfiniBand and some clients that are connected to the VAST cluster via Ethernet for those. So we can either do that with dedicated NICs on different CNodes, or in some cases, there are NICs that we put into the CNodes that are dual personality, where we can designate one port to be Ethernet and one port to be InfiniBand. So we can set those up as we wish. Regardless of what the setup is and how many CNode pools we have, though each one of those CNodes and each one of those VIP pools has access to and can make use of the performance of all of the DNodes in the back end. There is no segmentation of the DNodes. It is DAYS architecture, disaggregated, share everything. So the CNodes still see all the back end DBoxes, all the back end SSDs have access to all that performance. If we wish to go through and we wish to configure a VIP pool to only use specific CNodes, again, it's going to be very simple. We go into the VIP pool configuration, and when we create it, there's a slider that says, hey, use all the CNodes, which basically says all CNodes selected. We just turn that off and then select which CNodes we wish to use. So in this case here, I'm only using CNode 3-13 and 3-14 and not CNode 15 and 16 in this VIP pool. If I do have a situation where I've got those split personality NICs in the front end CNodes, I can select from the port membership whether I want to use the right port or the left port of those physical NICs for those. And again, the right port or the left port is going to be either Ethernet or InfiniBand in those cases there. Or even if they're all both Ethernet or both InfiniBand, you can select those there. So we've got plenty of different options for handling different network topologies. One other item on here too is that we may want to go through and set we may need to go through and have multiple VIP pools for different purposes. So typically when we create a VIP pool, it's going to have the role, it's going to be servicing out client traffic. So we're talking about NFS or SMB or S3 or for the VAST database, you would serve that. Out of that, when we create the VIP pool, we define a role. So the role is normally going to be set to protocols, which covers that client traffic. If we want to, especially on larger clusters, we may want to dedicate specific CNodes to handle things like replication, where we are replicating data out to another cluster, either for backup purposes or for the VAST global namespace usage, or for other types of replication, where we don't want to have that replication traffic affect I/O for other purposes. So we would create a VIP pool that is used strictly for replication, and that won't handle any other, won't handle protocol traffic for that. There's another one called VAST Catalog, which is used for catalog queries for VMS. Not very common, not very needed, but there's another option there as well. So any one of these can be bound to specific CNodes. We can have multiple VIP pools on a specific CNode. So even though we will have a replication VIP pool and a protocols VIP pool, these could actually reside on the same CNode. We just wouldn't get that isolation if one of those becomes busy for that. And so you need to be aware that when you're going through and having multiple VIP pools on the same CNode, there could be hotspots that might develop for that. The analytics are able to see that and show you that if those kind of things occur, but just you need to be aware of those there. So the question comes up when we're talking about VIP pools and multiple IP addresses. Client will typically connect to a single IP address. What happens if that CNode fails? How does the client react to it? Do they lose connectivity? What happens with that? So the normal operation here for things is, we have our client, they will connect to a VIP, a particular VIP within the pool. That'll connect to that'll be on a particular CNode. They'll do their reads and writes, and if they're accessing data, that will go back to a particular DNode. Talk to the write. The write buffer will be put into storage. The write will be put into storage class memory to later be compressed and deduplicated and all of those good things there. And eventually, or if they're doing a read, it may come directly from the hyperscale flash in the back end, but this is the normal flow of operations. To point out here is that any writes that are done, if there's something related to the state of the write connection, like in case of things like SMB or NFSv4, where you have an open operation and we need to track that, okay, this file is opened by this client, that information, rather than being stored in the CNode, is actually stored in the storage class memory saying, hey, this client has it open on this file. And the reason that we do that is that if we have a case where there is a CNode failure, and this could be either a CNode failure where there's a hardware failure of some sort, the CNode physically failed, or the NIC failed, or the port failed, or we took it down for administrative purposes, for, let's say, a code upgrade, we don't want to lose that state. So what will happen in this case is that the CNode goes down, the cluster detects the failure, the VIP address is immediately moved over to another available CNode. The client will go through and see just a very short pause. They'll see a TCP disconnect, reconnect that on that, but it's going to be at the TCP level. It's not going to be at a higher protocol level. So they see it no worse than, I had to do a retransmit maybe of some sort on the TCP level. But then they reconnect up to the new VIP, or to the new location of the VIP. It's the same IP address, none of that has changed. And any state that needs to be read as to what's going on for the transaction, that's all available to the CNode from the storage class memory. So if the open does not need to be redone again, the write doesn't have to be redone, any of that is all already in the SCM. So none of the state is lost. So we can go through and we can sustain writes, even surviving CNode failures for this. So these kind of failures are transparent to the clients. When we come back, when a CNode recovers, or in the case of even if we're expanding a cluster or adding additional VIP addresses or redistributing the VIP addresses across new CNodes in the cluster, the process is very similar. The CNode is detected as being online. The VIP address is moved back to that CNode or redistributed across the existing CNodes or the new CNodes that are added in. And the client, again, sees that very quick TCP disconnect, reconnect. For that, it's transparent. The state is still an SCM, and it just continues on without having any issues. So very efficient, very transparent to the clients. So moving on here, let's talk about the VAST DNS service. Obviously, we're talking about a collection of IP addresses. So a client will connect to one particular IP address, but how do they determine that IP address? We don't want to have a single lookup of a host name for this. And obviously, if you're looking at accessing something like Google or one of those network services that are out there, you don't know their IP address. You're going to connect up to a host name. So we need to have some method of doing that. The client will only connect to one VIP address, so we need to have multiple IP addresses behind a single host name for that. So you don't have all the clients going to that single address, or worse yet, having to tell all the client or be able to go through and in your clients, give individual clients individual IP addresses and have to manage that for them. We also want to be able to go through and do something to be able to distribute those connections across multiple CNodes so that we don't have those hotspots. So there's always been a couple different ways of doing this. The first option is to go through and put multiple A records into DNS for that. So you'd have multiple A records for the same host name, and that's an option. It works somewhat okay, but what happens is it depends upon the DNS server, where first off, if a client does a DNS request as a lookup, let's say vast1.vastdata.com, and they get back 8 IP addresses for that, that may confuse them when they're only expecting one. But more commonly, what happens is that many DNS servers will respond back with the list of IP addresses in the same order for every single client, and the clients will always go through and take the first IP address from the list. So if a DNS server is responding back with the same list of IP addresses in the same order, and the clients always pick the same the first IP address off the list, they're always going to go to that first CNode of the first entry, which gives you a hotspot while the other ones are sitting empty. So that's not very good either. The other issue is that anytime we go through and want to expand the VIP pool by adding in additional addresses or adding a new VIP pool, there's all this additional management that has to go on. So typical corporate environment, you have to go through and file a service desk request, because typically the storage team is not the same one that controls the corporate DNS servers. So you have to file a service desk request, get the entries put into there, go through, have them wait for that to happen, which could take a day or two or longer with that. It's somewhat of a big hassle to go through and do that, especially if you're adding in additional VIP pools or making modifications. So again, not quite as optimal, and additionally, you don't have control again over the ordering of things for that. So VAST has a DNS service that runs on one of the CNodes. This VAST DNS service that's there will respond to a host name defined in the VIP pool configuration. So in the VIP pool configuration, we can define, say, hey, this VIP pool, I want these VIP addresses to respond to pool1.vast1.example.com. So anytime I do an NS lookup of that against this VAST DNS service, I will get back one of those IP addresses. We also do some other things, like we can do virtual style bucket paths, and I'll talk about that in a minute. And these can be aliased out as well using CNAME records to go through and do this. But typically for this service, what we would go through and do is we would go through and delegate this out from your upstream DNS. So the way this would look is that you'd have your corporate DNS. There would be an alias of a subdomain. So in this case here, I would have an alias for vast1.example.com telling the corporate DNS server that any user or any client that requests information with this subdomain attached to it, refer that or direct that to the VAST DNS service. Excuse me, running on one of the CNodes. And that will be delegated to that. So what will happen is that when we go through and a client does the queries and doesn't know anything about the VAST cluster, it goes to the corporate DNS. The corporate DNS says, hey, you're looking for pool1.vast1.example.com. I know that anything vast1.example.com needs to be delegated off to the VAST DNS service. I will direct it to that. And then the VAST DNS service will respond back with one IP address from that VIP pool. The next time the next request comes in, it will respond back with a different IP address from that same VIP pool, or a third IP address from that same VIP pool. The VAST DNS service will by default send out or reply with one IP address from the VIP pool, round robin across all of the IP addresses in the VIP pool, until it's gone through all of them, and then start over again. For that. So we'll round robin out across those there. We do have options within the VAST DNS service on the server to return more than one IP address. There are some cases where that is beneficial to go through and do that. We can configure to return more than a single IP address where it returns 2 or 3. But in either case, even if it returns more than one IP address, the order will be different every single time. So even if the client only looks at the first IP address that's returned, it will be a different IP address for every single request, which helps us go through and do the balancing. So the way we set up the VAST DNS service on a cluster is very similar. We go under the network access, we look at the DNS tab from there, we define our service. So first off, we give it a DNS service name. This is just going to be a logical name to go through and look at. We can call it My DNS, VAST1 DNS, whatever we want to call it. We define the IP address that we want this DNS service to listen to for this, give it a gateway, tell it what DNS suffix it is going to be using for this. So in this case, in our example, we would use vast1.example.com. Provide a subnet mask. If we need to run on a specific VLAN, we can do that as well. We have some controls over where this service runs. By default, it can run on any one of the CNodes, but we have controls as to where that would run. We can also select where we want this to run. By default, under the port type here, we've got options to go through and run this on the VAST management network, which is a network that is used for management of the VAST services, which may be isolated from other things. It can run on the northbound network, on the client-facing network as well. And then we have a time to life value that we can go through and set on this. For any response that we give, we'll set a TTL value along with that response to tell it how long we can go through, or how long an upstream client can cache that. So let's talk about that in just a minute here for that. So once we get the DNS service in there, we can go through and go back to our VIP pool, and we provide the VIP pool domain name here, give it a name here, and it will automatically go through and tell us, hey, this is now the DNS FQDN that we're going to respond to for this. And this will be updated every time I update the VIP pool or I add a VIP pool. The VAST DNS service will make use of that information and automatically be updated, be able to respond to any one of those addresses for them. So very, very fast, very, very efficient. Does not require you to do any, aside from the additional delegation record that you report in your corporate DNS to point to the DNS service, there's no other operations that need to be done. Now, again, to point this out, using the VAST DNS service is definitely not a hard and fast requirement. It's a configuration option that you can go through and do that will simplify or possibly simplify administration of things, but it's not a hard and fast requirement. So let's talk a moment about the time to life for this. So there is a TTL that we can define within the VAST DNS service, which means that any request that goes out, it tells it how long that request can be cached for. So your typical DNS server that is out there wants to go through and attempt to cache addresses, so it doesn't have to do subsequent lookups every time there's a query on something. So these time to lives could be a few seconds, they could be a few minutes, it could be hours, depending upon what the address is and where it is. But in this case here, because we want to give clients different addresses every time there's a request made, we want to make that TTL as small as possible. So if I have 5 clients that all do a lookup of pool1.vast1.example.com, we want to make sure, or want to try to get those different IP addresses, their connectivity is spread out across all of the CNodes. So to do that, if we can do that, we don't want to have that to be cached. So we would typically set the TTL to 0, which means do not cache the results at all. Now, the problem is that some DNS services do not enforce a TTL of 0. They will not honor it, and they'll default to 1 second. Windows DNS server, if you're using that with Active Directory, that is what their defaults are for that. So that generally, depending upon what your workload is, that may or may not be a problem. But in the case of like a campus network where you have different users that are connecting to the VAST at different times, if you have 2 or 3 clients that connect during the same second or do a lookup in the same second and get the same IP address, that's fine, because there's 50 or 100 or 1,000 clients connecting to the VAST, and it's not going to make much of a difference. But if we're looking at, let's say, an HPC cluster or something, or an AI cluster where you're going through and having multiple clients all start up at the exact same time, do the same DNS lookup at the same DNS server, if they all get that same IP address back because it's all within the same second and it's all cached in the same thing, that will give you some issues there. So something to be aware of. It's another configuration option to consider. When we're talking about S3, there's another thing here, and I mentioned this earlier, is that the VAST DNS service does have the ability to support virtual hosted style S3 bucket names for this. And basically what these are, if you're not familiar with it, is that the bucket name is attached to the endpoint for the FQDN that is looked up. So in this case here, if I've got an S3 bucket called my bucket on that VIP pool, I could do an NS lookup of mybucket.pool1.vast1.example.com, and the VAST DNS service would actually respond to that with an IP address from that VIP pool, from the pool 1 VIP pool, which is, that's pretty cool because I haven't defined anything other than to do that. So typically this is leveraged with S3. Really, any name that we put in there could be used. So I will do a lookup of pool 1. I could do a lookup of random918.pool1.vast1example.com or abcdef.random918pool1vast1example.com, is that the VAST DNS service will match the suffix or the pool name on there to give IP addresses for. And this can be used not only for S3, but for other purposes as well. So one of the best practices that we have for VMware services is that if we have multiple data stores, or we're hosting multiple data stores through the same VIP pool, if we go through and we mount via the pool name, the VAST pool name, VMware would go through and do a lookup once and say, oh, that is going to be this address, and then all of those data stores would come from that same VIP address. Not optimal, it would be a single bottleneck in there, could be performance problems. But if I were to append, let's say, some random data store name to it, or the name of the data store that I'm naming in VMware to the address, random 918 for the data name, I could go through and have each one of those would be a separate DNS lookup, a separate host. It would be treated separately as different IPs of that. They'll all be part of the same VIP pool. And because we don't care which IP address is used on the VAST side, they would all be they would all be able to have access across, and that access would be spread out across the existing CNodes. So it's leverageable not only for S3, but as for other things as well. So one of the limitations here is that we would have to go through, we're talking about using certificates for S3. We need to make sure that we encompass that for these there. Make sure that any S3 certificates that we use when we're utilizing this handle those wildcard type addresses to allow for S3 certificates coming in. So moving on here, let's talk about the different client access options. So how do we get the best performance? So we talked about a single connectivity, a single client connecting to a single VIP address. Can I make use of more of that bandwidth that that VAST cluster has? What are our options? So let's talk about some options here with this. So the VAST, with client access for NFS or SMB, we'll talk about S3 in a moment, we have your traditional mounting options. This is going to be normally what people have done for many years with this. You have your mount option. It points to a single VIP or single IP address to a single host, and that works just fine. You get a single TCP connection across a single TCP port, and you're able to do I/O. This works for NFS, works for SMB. The issue is that TCP as a protocol maxes out at about 2 gigabytes a second. When you factor in things like the acts that have to be done for every packet that gets sent and the ordering and things like that, just latency there, it limits out to 2 gigabytes a second. Even if you have a 100 gigabit connection or a 400 gigabit connection, a single TCP session will max out at about 2 gigabytes of data per second per host. That's the rules of physics. The rules of the way TCP operates. It's nothing specific to VAST. So realizing that, there have been changes, there have been things that have been in the Linux kernel for a while where it's like, well, why not open up multiple TCP channels? So the changes were put, there were things that are added to the Linux kernel where we can use what's referred to as NConnect to open up multiple TCP connections to the same IP address and treat them as one connection. It gives us a little fatter pipe, and we can go through and throw more I/O on. So this is present with Linux kernels starting with version 5.3 and up. For that, there's an option called NConnect we can use for that. This is also available with SMB with multi-channel. It does make leverage of this as well. And for this, we can get about 90% port saturation. So we can get about 10 gigabytes of throughput on a 100 gigabit connection for that. So we get about 90% there. The cost is that this can be somewhat expensive on CPU load just to manage those TCP connections, but it's very common, doesn't require anything special to go through and do that, especially if you're running a more modern version of the Linux kernel, or a more recent version, recent being relative. Another option here is to go through and utilize multipathing. So maybe I've got more than one NIC on my host. I certainly have more than one CNode, so I want to leverage all of those. So if we're able to go through and leverage multipath and use both of those ports and NConnect to give us more than one connection, more than one TCP connection on each one of those IP addresses, I can get even more throughput. So I can go through and I can saturate these ports from the client, where the limit is going to be the client throughput, or what the client can physically do in terms of their network ports. But I could get up to about 30 gigabytes a second on 100 gigabit links. So we're able to pretty much saturate these two connections between these two here. The cost of this is that, again, because we're doing multiple TCP connections to multiple CNodes and things like that, we're using CPU to manage those TCP connections. So to control some of that limiting, to control some of that CPU usage, there's an option of using RDMA. So RDMA will do a direct memory transfer from the client to the CNode of the IO that needs to be done, and kind of avoid some of that TCP, the TCP congestion on the X there. It makes some assumptions on the existing network that it can handle the RDMA, and it's not going to be losing packets, so there's no retransmits there. But even with that on a single path, we can get much better throughput with RDMA on a single path for a single port, where we can get about that 90% port saturation with virtually no CPU utilization on that, because we're doing direct memory transfers for them. And ultimately, if we go in NFS or we do RDMA with multipath for this, we can get this out across, or we can get these 50 gigabytes a second of transfer rate, between a single client and a VAST cluster. And these are numbers that we can validate and demonstrate today. Now, when looking at this here, this is standard Linux kernel right now. Both of these options here. Some of the very most recent Linux kernels have added in multipath functionality. RDMA is not common; it's not baked into the standard Linux kernel. It's as a multipath here is not typically baked into the typical, or because RDMA here is not baked into the typical kernel as well. So we do have what's known as the VAST NFS driver to give you that kind of functionality. We'll talk about that in just a second. So again, just to review, NConnect, this is a standard mount option for Linux clients. You can set up to 16 ports for that. You just say mount -O, NConnect equals, and then some number there, and we can go through and the client will establish more than one connection. Again, baked in the Linux kernel 5.3 and higher. These will all go from the same source NIC to the same IP address on the CNode. Now, if you wish to be able to use RDMA over NFS and get that additional multipath functionality for that, along with having NConnect and things like that, you can utilize the VAST NFS driver. This is an optional NFS driver, replaces the standard NFS module from the client. It is compatible with existing NFS solutions, so it doesn't change how NFS operates with other types of NFS storage. It just gives you additional options to be able to leverage VAST storage and multipathing and all those things there. It is open source. You can obtain this from vastnfs.vastdata.com, and you can download that, compile that into your system. It provides you with the RDMA support and the TCP support, not only for current Linux kernels, but older Linux kernels as well. So you can get that additional functionality on pretty much any current Linux kernel that's out there. It doesn't have to be the bleeding edge versions that are there. And we just specify things here using some additional options. So with the VAST NFS driver, there's an option here called remote ports. And the remote ports, we just specify how we want that multipathing to be spread out across, this case here, we're spreading it out across 16 IP addresses, which would, if we're doing 2 IP addresses per CNode, be spread out across 8 different CNodes in the front end. So we would be able to get that additional throughput and support all under a same mount. So if you have interest on this, go through and look at that in the from the web page there. It is open source. You're free to compile it, download it, use it as you will for that. I will point out that the Linux kernel itself, like I said, the more recent versions do have multipathing available to it. It functions a little bit differently than how the VAST NFS driver does, namely that it goes through and you establish the initial mount, and there's additional commands to add additional paths after the fact. The VAST NFS driver has the advantage of, number one, being able to specify that all on the single mount option, but it also adds an RDMA support. So it will give you the maximum amount of throughput. Now, just be aware that generally, depending upon what your use case is for this, you may not need any one of these. The vast majority of our customers using NConnect is more than enough. Your individual Linux servers that are mounting things don't need or can't take advantage of all that bandwidth there, so they don't need to have that NFS driver in there. HPC solutions and things like that, where you absolutely need to have the most amount of bandwidth to each client for that would. But this is another option that is in there as well. When it comes to S3, S3 already is kind of designed to be able to take advantage of these multiple channels. S3 is designed for slow internet-based links for this. So, they know that a single connection might get reset, might get dropped. There may be other ways of getting to a client. So S3 typically, if it's using parallelization for that, which is normally the default for S3 uploads, it'll break up any particular upload into multiple parts and do a multi-part upload, and the client or the destination system reassembles those. So it already benefits from that. There's really not any additional modifications that you typically have to do for an S3 connection for that. So that's good there. The one thing is that with S3, when it does the lookup of things, it typically will do a single NS lookup and use that address for all of those connections on that. So that still would go to a single CNode with that. It may or may not be an issue. Normally S3 is not as equally concerned about throughput if we're coming across the internet for that. But if you do want to go through and get the most amount of performance from a single connection there, then there's things that you can do with an external round robin DNS or some other load balancers in there. But normally S3 tends not to be that much of an issue for. So with that does conclude my presentation for today. I do appreciate your time on this. So very, very glad that you could join us this evening. Hopefully we've answered all of your questions about the, hopefully we'll answer all of any questions that you have on this. And I appreciate your time, and thank you, and have a good day. Bye now.